Hello, this video we are going to discuss a question from FM18, paper 42, which is regarding X-ray imaging and the decibel ratio of X-ray intensity. So let's go. Number 1, suggest 2 causes of the lack of sharpness of an X-ray image. So to have good sharpness, right, there are a few properties that the imaging system should have. Okay, I will list down all the possibilities, but you only need 2. Okay, so the first thing that could happen is that the anode area is large. All right, if you haven't checked out the video that we have explaining how to get sharp X-ray image with good contrast, go find it in the playlist. Okay, so the anode area is large. Okay, or okay, this 1. I'll put this one as 2. Then the second thing, it could be the scattering of X-ray beam. So the X-ray beam collide with the certain parts of the device and it scatters. Okay, so this is what happens when you have no lead grid. So the lead grid is how we decrease the amount of X-ray scatter. Okay, and of course the anode area is too large. Third possibility could be the lack of collimation of the beam. Means the hole that the X-ray come out from, the aperture, is too large. So you want to get a good image, your anode area must be small so that the X-ray beam is focused. You have to use a grid so that you don't get any stray X-ray photon pinging at weird direction, causing some background scattering. You also need to kind of like collimate the beam, okay, by making sure that the aperture is small. So the one that I put in bracket there is the problem with the setup. Okay, and this is what is happening to the X-ray. So scattering of X-ray beam, the bracket here, is due to no lead grid and lack of collimation of X-ray beam due to aperture being too large. All right, and the final and the fourth thing that you could write has to do with the photon. Okay, so the X-ray photon energy is too low. Or you could say the X-ray is soft. So this one, the reason why you don't get sharp image is because instead of penetrating the tissue or the structure properly, you absorb everything. So it's like, what's the point of the X-ray, right? So the X-ray is soft. And the reason for this is, okay, I'm just going to write this one. This is due to accelerating potential, remember? So this one would be due to the low accelerating PD. I'm giving you a bit extra here, way more than is needed to answer the question, because this is a general question. What causes the lack of sharpness? You can complain about the X-ray, you can complain about the experimental setting. Okay, so everything at the back here, no lead grid, aperture too large, low accelerating potential, all this is the setup problem. So if they say suggest 2 causes in setup of the X-ray beam or the experiment, then you will write this in the bracket 1. Or you could say it is found an object image is not sharp enough. This is due to the scattering of X-ray beam. Suggests an improvement. You put law. Place a lead grid. Okay, so this is the steps to improve, and these are the problems. Okay, steps to improve are in the bracket. All right, so this kind of facts, you can watch the video to understand them better, but it's good to know more than one. Okay, because they could ask you a specific one. All right, so that's it. We're going to move on to part B. The thickness of a sheet of metal is examined using a parallel X-ray beam as shown or as illustrated in figure 12.1. Okay, so you have 3.2 mm here. Here to here is 3.2 mm. And then you have the distance x. Okay, so the thickness is different. Part of the beam passes normally through 3.2 and another part passes through XMM. Linear attenuation absorption coefficient, which as Miss Ellie would like to call it, mu, for the X-ray beam in the metal is 1.5 cm -1. Okay, the ratio of intensity of X-ray beam transmitted through 3.2 mm of metal to XMM of metal is found to be 0.81. Okay, calculate the thickness of X. Okay, so this kind of question, right? Step 1, what you need to do is actually to write the linear attenuation equation. Okay, so the attenuation equation, are you ready? Okay, it is I is equal to I naught, which is the initial incident attenuation. I naught is here. The one that passed through will be I. The one that passed through here is also I. Let's say this one is Ix lah for XMM. Okay, so the equation I is equal to I naught E negative mu X. All right, so we're going to look at this equation and think about the ratio. It says that the ratio of X-ray transmitted to 3.2 is 1, and X-ray transmitted to XMM is 0.81. So I will say that I for the 3.2 mm over the I for X is equal to 0.81. But to start with that, we need to be able to write the equation. No? So we're going to substitute the equation now. This 3.2, don't worry, if the equation is new to you, just use it carefully. So this equation will be I naught E to the negative, what is our mu? 1.5 cm -1. Okay, I need to point out something first. This is cm -1, this is mm. They have to have the same unit. Your mu and your x must have the same unit. Because if your mu and your x are not the same unit, you have to convert one of them. Okay, so a note here when you use the equation, mu and x will have the same units. Okay. All right, so right now we will substitute the value of mu, which is 1.5. And I think I'll just change the 3.2 mm to cm, which is 0.32. Okay, divided by I naught E negative 1.5, because it's the same material, so the linear attenuation, mu, is the same. We are looking for x, and this is 0.81. I'm going to draw a line here. Okay, so the first thing you will notice is that your I naught can cancel out, so I'm just going to cancel the I naught, okay? And then what we have here is two exponents. So to solve these two exponents, we do step by step, okay? Right now, we will have e to the power of negative. Okay, I'm going to press my calculator for this part. So if you know how to solve the equation, you may go ahead, okay, and skip some steps. If you don't know, it is totally fine to take your time. So this is negative 0.48 over e to the power of negative 1.5x. And this is equal to 0.81. I am going to borrow the logarithmic identity. I'm going to pronounce the word because I'm just going to use the identity of a to the power of, hang on. This identity is x to the power of a over x to the power of b will be equal to x to the power of a minus b. Okay? Example, if you have x power 3 over x power 1, it will be x power 3 minus 1, which is x squared. So if you always forget your index, you can do this kind of thing to testing. This one is to test, okay? But if you don't need it, that's fine. You can go ahead and proceed. So right now, this will be e negative 0.48 minus bracket negative 1.5x. And this will be equal to 0.81. Okay? So I will clean up the exponents first. Or rather, I could bring the exponents over to multiply, but I'm just going to clean it up a bit and do it step by step so you can see. Again, how many steps you write is really up to you. All right, so right now, what I have here is E negative is positive 1.5x minus 0.48 is equal to 0.81. So you can bring the exponent over. All right, so the identity that I'm using, just going to draw another line here to show you. Let's say you have e to the power of n is equal to a number k. What you will do is you will ln both sides. You will ln e here. This will be equal to k. And this e to the power of n, this n can bring down. So n ln e is equal to k. Ln k. Ln both sides. Okay, you add ln to both sides. My bad. So when you ln both sides, you ln one side, you ln the other side, you get n ln e equal to ln k. But what is n ln e? This is 1. So n bracket 1 is equal to ln k. All right, so thank you for your patience, for waiting, okay, because some people may struggle with this part. So if you have an exponent like this, ln both sides. Okay, so I'm going to do everything step by step. I will ln both sides now. This will be ln bracket e to the power of 1.5 minus 0.48 is equal to ln 0.81, ln both sides. So what I have now is 1.5 minus 0.48. The n I bring down. This value of n is moved downwards. So this is the n. We move in front of the ln. Ln e is 1. Okay. Where did my x go? Did it go for a walk? Let me put it back in. So 1.5x minus 0.48 is equal to ln e. Whenever I run out of space, my working will be all over the place already. Because normally I don't need that many steps. All right, so where was I? Okay, so I ln both sides and this exponent is brought up. What I have now is ln e is equal to ln 0.81. Okay, so this ln e will become 1. And then 1.5x minus 0.48. Ln 0.81, can press calculator. Okay, there's a ln button in your calculator. Make sure you press that. This will be negative 0.21. Okay, so it's getting a bit messy. Let me draw a boundary around here. Okay, so then I can just choose to move things around and solve for x. Finally, I will have a value for my x. That would be 0.48 minus 0.21. I guess you could put 211, doesn't matter. Divided by 1.5. Okay, so you solve this, you will get 0.18 cm. But the final answer wants this in mm. So please change this to 18 mm. That will be the final answer. Okay, so all the identities that I have here, all this is something that you should already know at this point in your studies. Okay, if you don't, inside the channel or the stream, there will be playlists for you to watch where Miss Ellie will record the log and ln identities for you. Okay, so make sure you really know how to move and manipulate this, especially if you don't have mathematics as your subject, because if not, you will be quite the confusion. All right. Okay, we're going to move on to the second part now. Okay, so this is the second part. The ratio of the intensities is also known. So ratio of the intensities is also the ratio of power, okay, of the X-ray beams. Calculate the ratio in decibel. So I'm going to define decibel for you right now, because technically if we follow the syllabus, you will know what decibel is in chapter 16. But because we rearranged the syllabus so you learn chapter 16 at the end, So let me explain what decibel is for you. Okay, one bell is log I1 over I2. So it's just a different way to ratio the intensities. Normally, we divide just like this. We just divide like that, and then we get a ratio 0.81. Means that the 3.2 mm one will be 81% less than the XMM one, because the 3.2 mm is thicker ma. So this one will be about 81% less intense than IX. Okay, but sometimes we don't directly ratio the intensity. We log scale it. Examples of using the log scale is like pH. So for example, in your chemistry, right, your pH of your solution, you get pH 8 point something, 5 point something. pH of a is equal to log concentration of hydrogen atom. This is the definition of pH. Okay, so right now we have to understand the definition of Bell. So in sciences, sometimes we log base a certain ratio or log base a certain number. For what purpose, you may ask? Why do we need to log here, log there, chop so many trees to log? Okay, so the reason why there are logs, okay, is because, number one, we are going, okay, I'm not sure what technical error happened just now, the whole page jump, but we're back. So Bell, as mentioned just now, is a log-based ratio. Example of using a log-based scale is your concentration of H plus for the definition of pH and whether something is acid or base. There are a few reasons why we want to use log scale, okay? The main reason is because log scale can be linearized easily. This is log base 10. So when there's LG here, it's not the fridge, it is log base 10. Okay, in your calculator it should look like LG. And the second reason beyond linearing, which is the main reason why we are using it here, is because when you log something, the numbers, it can give you more information. Number one, positive or negative to show relative magnitudes. Okay, number two, the numbers can be a bit manageable. So easier to plus or minus or times divide, so manageable. Especially if the number is too big or too small. Okay, you will know this when we do the log and log question in paper 5. So if let's say you log a very big number, like 1 million, you get 6 point something or 5 point something or 7 point something. But if you talk about 1 million, then that's 6 digits that you need to deal with. Okay, so here 6 or 7 digits you need to deal with. So here, right, we are going to log because to make the numbers more manageable. You try and see lah. You go and log a very, very big number, you get a smaller number which is manageable. You log a small number, you get a negative number, but it's still a number that's more manageable. Plus and minus will show the magnitude because I say this because if you log something, let's say this is log x. If x is greater than 1, then you will get positive number. Okay? If x is less than 1, but still between 0 lah. Is it right? My log graph. You get a negative number. Yeah, my log graph is right. So you might be thinking, what if x is equal to 1? If x is equal to 1, then your log x is 0. Press calculator and see lah. Okay, so this positive and negative number allows us to know which magnitude is bigger. Because if x is greater than 1 and you get positive, this means that this ratio up here, this I1 is bigger than I2. If x is between 0 and 1, that means I1 is less than I2. Okay? If you get 0, it means I1 is equal to I2. So you can show the relative magnitude. Okay? X cannot be negative. It also cannot be 0. Okay, so press your calculator, it will tell you stuff. So in this case, right, if you want to calculate decibel, since 1 bell is log I1 over I2, then decibel, decibel, so I'm just going to write deci here. This deci is 10 to the power of -1. Okay, so you bring it over, decibel, or short form dB, is equal to 10, because you bring the 10 over, you bring the deci over ma. So bring this over here. So 10 log I1 over I2. So this is how you find the decibel. 10 log I1 over I2. Okay, so we can use this here if we want. Okay, so this ratio, now if you want decibel, this will be 10 Lg, the ratio of intensities, which we already have. So it's 10 log 0. Check here lah, the ratio we already have here, 0.81. So 10 log 0.81. Just press your calculator. So by pressing calculator, I will get negative 0.92. So this negative tells me that the incident ratio is bigger lah. Okay, in this case 0.81 is still a more manageable number. So although the second reason doesn't really hold here, but the first reason still hold lah. When I see this, I know. But of course, this 0.81 also can tell you the information lah. All right. So what the purpose of introducing decibel to you is, sometimes if they ask you to calculate the ratio of decibel, you will use this relationship. Okay, 10 log ratio of intensity. 1 bell is 10 log I1 over I2. Deci is 10. Okay, decimeter, centimeter, 10 to the power of -1. All right, and the log scale is something that you may have used in science previously. Okay, and this question is just using the attenuation equation. Don't feel shy if you need a bit of refresher for your indices. Okay, your index and your identities. All right, if not, if you are good enough with this, you reach this part, or you can press calculator already. You know what to do. You don't have to continue here. All this will happen in your brain. All right, if not, then it's okay to write out all your extra steps. All right, so that's it for this question. All right, so hopefully you'll be able to try some other past year questions to help you solve it. Okay, the bulk of the calculation is here. We care about how much intensity, or how much is the intensity of the X-ray photon, so that will allow us to image better. Okay, that's it. I'll see you in the next video. Take care. Comment or ask questions if you have any. Like and subscribe as usual. Follow the channel. I'll see you. Bye bye.